Do you think this thing just diminishes by half, by half, by half, by half, by half, by half forever? At some point you get down to that last molecule of Samantha you, right? And at some point or another, that last molecule is going to decay and turn into some other things. And at which point, you really do get down to 0 grams eventually. Okay? So, again, we have this idea that we have modeling, and this decay model works really, really well for a while. Maybe even for a long time, but not forever. Okay? I want to do one more sort of example, but I want to talk about just off, you know, kind of on a tangent here. Y'all have heard of carbon dating? We use it in geology and archaeology to date how old something we believe something is, right? Okay, carbon dating is based off this decay sort of model here, okay? There's a certain isotope of carbon called carbon-14 that is radioactive, but it is present in all organic material. Okay, anything that was ever living has carbon-14 in it while it's alive. Okay, I have carbon-14 in me, and unless you're undead, you have carbon-14 in you, and plants have carbon-14 inside them, and so on. But when that organism dies, that organism stops producing carbon-14. Okay, so I'm an archaeologist or something like that. I found this layer of rock. I find a fossil or something like that, and I want to know how old is this fossil. Well, I find something else in that layer of rock that once upon a time was organic. And I calculate how much carbon-14 is present at that time. And I know that the half-life of carbon-14 is about 5,700 years. And I work backwards, and I'm able to calculate, I'm able to approximate how old this layer of rock is based on how much carbon-14 is present in that sort of fossil record. That's kind of sort of how that works. There you go. It's math in the real world. That's where people use radioactive decay. Some of them. Most of us don't.